All right. So thanks everyone for signing on. This is the first lecture that walks through all of the 10 chapters that we've studied so far, starting from scratch. Um, Resume. Okay. All right. So thanks everyone for signing up. So the agenda for today is basically a walkthrough of the textbook, um, walk through the chapters that we've done. But before that, give you sort of insights into why the statistics that we study from this textbook is really important for machine learning. What applications it has, what are the various connections that it has to things that you might already have read or know about, or in at least some of your cases when you worked with machine learning, I am fairly sure that you've done things that you thought of in a sense that, okay, I understand this somewhat, but like why, and what assumptions you make, which we typically don't tend to think of. And that's one thing this textbook particularly does really well. He explains in very plain English why some assumptions exist, why people don't talk about these assumptions, and most importantly, what do you do when these assumptions fail. So, with that, let's get started with a bit about the textbook. Um, Going chapter wise, the first chapter harps on these concepts. It sort of assumes an understanding. So it has a sister textbook that is basic statistics, and this is the slightly advanced version of it. So we don't go into the other textbook because that is a bit too basic, and it's mainly like a first year level course, and this is more of a grad student or a master's level course, and you typically want to punch above your weight when it comes to statistics, um, or when it comes to life. But anyway, feel free to interrupt me at any point if I mention. So I've tried to do is add some context to every bit of jargon that I use. But if I'm ever assuming some knowledge that you don't have, interrupt me, stop me, and force me to explain that concept to you. I might do a poor job, but there are others on the call smarter than me who can correct me. All right. So, what is linear regression and why is it important in life? So far, a lot of you have worked with deep neural networks. Most of you have heard of large language models, large um, graph neural networks, large CNNs, RNNs, what have you. But the fundamental idea of regression, and the reason why it is still so widely used despite the existence of these more complex models, is because it's simple, it's straightforward, and it's interpretable, for the most part. So again, to start from the ground up, like statistics, you have these concepts of random variables, you have concepts of expectation, variance. To start again, right at the bottom, a random variable is basically equivalent to like a coin flip experiment or any experiment that where you can have multiple values for the outcome. um, you hit someone, they can either hit you back, they can run away, they can pay you money, whatever. Multiple outcomes for a particular experiment. So this set of values that we associate with an experiment can be expressed in the form of a random variable. So a coin flip is the simplest example that most textbooks typically use. The outcome of a coin flip can be heads or tails. So you can represent that with a random variable corresponding to 0 or 1 for heads or tails. Um, and this set of values that a random variable takes, in a sense, defines its distribution. So once you have if you plot on the x-axis the index of the experiment, and on the y-axis you plot the values, you can sort of get this plot of a distribution of a random variable. Well, not really. The x-axis is the I'm thinking of a histogram. Okay, so not going into too much detail there. I assume you guys know what a random variable is. The expected value is, using the English definition, roughly the value you would expect the variable to take. So mathematically, the expected value is the mean. And using the distance of, do I want to get into mean and variance? No, I don't. I want to talk about regressions. So I will get into regression basics. Um, this chapter basically focuses on why a linear regression matters in life. It gets into the math behind linear regression, and it tells you about what what are the assumptions you're making when you're saying your y is equal to w times x, where w is like this weight matrix, x is like the data you have, which is also called the features or the covariates, and y is called the target variable or the response. So when you want to find the optimal set of weights that you multiply with your features to get your response, there are certain mathematical nuances involved. And it's essentially like saying, if I have a set of data and I want to make a prediction, like if I have the outcome of um, individual incomes and I want to make a prediction about GDP, to some extent it's just math, but to some extent you can make predictions because there is some randomness involved in markets. Or I'm not a financial analyst, but something like that. And there is a certain idea of a minimizing of a loss function, where a loss is just defined as how far away you are from your target variable and with your current prediction. And at each step or each epoch or each iteration, you want to get successively closer to the true value that you want to be able to predict. So that's about it for this chapter. And the main takeaway for that is that he has a lot of insight. He has a nice writing style because he's obviously really witty, but also offers like perspective on the appropriateness of some assumptions and crucially the failures of some statistical techniques. So after that, we get into more about breaking down these assumptions, breaking down these implicit sort of nuances that get into regression. So if you're if you're working with a linear model, without, like, at some point you believe that the true model, like the true um, okay, I should step back first. So the reason pattern recognition works is because we assume that there is some pattern to be found in the world. So, like, there is some actual pattern in the world that we are looking for. If there is no real pattern in data, then we're not going to find anything, or whatever we find will be useless. So, the broad umbrella of the most important assumption we make in life is there is structure. If there is no structure, you can't do anything. So with that assumption in mind, if you use linear regression, at some point you are thinking that there is some true model for the world that is a linear model. Like, because if you consider a linear model, you're not going to be doing really well if the true model is really complex and non-linear. So that one bit is the assumption that the true model is linear. The rest of the chapter, we revisit the theory, the assumptions that the data are uncorrelated, by which I mean when you collect one data point, that has no influence on your collecting the next data point, and which has no influence on the third data point. So it also ties in with this idea of IID data, which is independent and identically distributed um, sampling. Sorry, not again. I haven't explained what samples are. Um, Samples can be explained as draws from a particular process, random draws. So if you go to people and ask them for their voting preferences, you're collecting a certain sample because you're not going to be able to go to everyone, but you want to be able to know what everyone is saying. So you go to some of them, you assume that if you randomly sample from whatever locality or whatever state you go from, or even at the country level, if you randomly sample, you're going to get roughly a good idea of what everyone is saying. So that is essentially what sampling is about. And so you assume in general in machine learning also that your data are IID samples, which means they are all drawn from an identical distribution and they are independent. So it's not as if you go to one person, you collect a sample. That means you will not go to this other second or third person. No, that it is completely random. And that is super important and super hard to do. Like this idea of why can't we get the true number of COVID cases is because random sampling is hard, because you can't just expect random people to come up willingly and take the COVID test. You healthcare workers will be happy to take the test. People maybe in the interiors won't be as happy. They'll be like, no, why are you poking your syringe in me? I don't trust you. So the point is, in life, random sampling is one of the hardest kinds of sampling, perfectly random sampling. So anyway, there are certain truths about linear regression, and the largest truth is like some questions about the real world are just unanswerable because we have limits on the data we collect. Yeah, so that's chapter 2. Chapter 3 gets into some ideas about statistical models. What is their relevance to us? um, what do we use them for? So again, getting at this point of, there is a world, the world has a structure. We want to make our assumptions about the world such that we can build smaller models at a smaller scale about the world, and they can still accurately model the entire world. And it's a little annoying because people use the word model in two senses. In one sense, a model is like your linear regression model, which is a noun, like the machine learning model that you use. And in the other sense, it is a verb, where you use a model to model the world, like um, where modeling is an activity where you represent the world in a certain or at your scale. So yeah, just highlighting that it's a little annoying. I understand that if you get confused about how I use the term model. Anyway, so this chapter focuses more on like what is a good model, what is a bad model, how do we pick good or bad model. So cross validation, model selection, what is overfitting from a very technical perspective, and how can we avoid it. And once you actually built your model, how do you check whether it is the correct model or not? But anyway, um, chapter after that is more about smoothing. So I told you that there is a world, we assume there is structure in the world, but now we have only data points. You don't have the lines connecting that data. And I'm talking about only in the linear sense. There could be more complicated data, planes, surfaces, and so on. But for now, let's restrict ourselves to what's called univariate case. Yes. Yeah. Um, so what I was talking about was, so far we've used linear regression, but there are other ways of fitting the data. And in general, when you fit a curve to the data, or this curve fitting is basically a way of smoothing the data. Because in a very simple sense, you can think of data as points and you're fitting a plane to that point. So you're like smoothing it over. And the degree of the smoothing depends on the curvatures. And so there are different ways that you can fit curves to these points. And this chapter looks at some nuances about curve fitting. Um, One important point is like after that, we get into this idea. So in a linear regression, what you're saying is if I have 10 columns of data, I will add one coefficient per column and multiply that with each data point to get a prediction. If anyone at any point has a question, stop me, ask me again, because I started off with a really poor um, explanation, but I'm getting a little better at things. But I might have missed some fundamental aspects that you're not aware about. So please unmute yourselves and ask me. Um, and I can also go over concepts. This is supposed to be a discussion, not just me lecturing you guys. Anyway, I'll get back to what I was saying. So linear regression is one way of smoothing. There are other ways of smoothing. And in a very simple sense, you can think of how do you pick this curvature. One way is to set this bandwidth, and by bandwidth what I mean is if you want to draw a line through 2 points, you connect the points, right? If you want to draw a line that's close enough to if you want to draw a line through 3 points, if they're in one line, you can draw the same line. But if they're not, then you can draw different sets of lines that pass through either any two of the points. And you can imagine as these points get more, this line changes. So what I'm saying is, if you have like 100 points, you can pick one at a time, two at a time, three at a time, four at a time, 100 at a time. And if you pick 100 at a time, you're essentially drawing a linear regression line through it. But if you pick less, then you're drawing individual lines and then connecting those lines across all of these points. So this set of points that you select is called a bandwidth, and you're essentially smoothing over those bandwidths, um, over that bandwidth. But anyway, so those, and how to pick this bandwidth is another big question that the chapter answers. So we get into that, and that's gets to this kernel regression. Someone said something. Oh, Namal, you're unmuted. Okay. So that is about chapter 4. Chapter 5 is about simulations. So typically in statistics, the way we conduct our studies and all of that is we say, okay, let's build our own world, then simulate our own data from this world, and then fit a model and see how well this model is doing. The advantage it gives us is we control the world now. So we know the truth. And because we know the truth, we can compare how well our model is doing with this ground truth. And you might ask, but in the real world, I won't know what is the truth a lot of times. And like, I don't control the world. And you're right. But the way we test it is to make this world as real as possible, fit our models, check our models, and then deploy those models in the real world. And to some extent, the argument is that is really the best we can do. Like, what else can you do? Who's going to tell you the true values in the real world? Like, whoever created our world clearly had no obligation to tell us how it works, and we're figuring it out ourselves. So that's the idea. You create these tiny worlds, you simulate your data, and with that data you fit your models, and then you do things in this tiny space. And when I say tiny, I don't mean like literally like just less data. You can still simulate infinite data in this tiny world. It's just that you control everything, and just for the visuals, pretending that it's tiny. Anyway, so that is like the idea of simulation. And even in simulation, you have the same thing. You have to make some assumption in your models. You have to test those assumptions. And at the end of the day, what you want to do is, once you've fitted a good model, you can use that model to simulate more data and say, if this model is a good model of my tiny world, then the data that I get from this model as a simulator should match the data I get from the tiny world. Are you clear on this?
Yes.
Okay,
Yeah, yeah.
thanks. It's really nice to hear people unmuting themselves and talking. Other than myself. So the point is that this idea is very powerful, and I'll get to that as we get into the next chapter. But that is this idea of simulation and how we can test if a model is actually representing the world really well. From simulation, and because this idea I mentioned of use a fit some model to the data, use that model, the simulator, simulate new data. A really smart dude called Bradley Efron came up with this idea of, okay, now if we only have some finite data from the real world, what is the best we can do? We don't have the ground truth. We just have this set of values, and we want to fit a model to those values. And what he said that we could do was the same thing that I just explained, that fit a model to this set of data, simulate from that model, fit a new model to the simulated set of data, simulate from that model, fit a new model to the third set of data, simulate from that, and keep doing that until you get a certain convergence in the data sets that you're simulating. So again, the argument is like, what is the best you can do? And you don't have any metric to evaluate. So you create this set of sequential simulations fits, or estimation procedures. So when you're fitting a linear regression, you're essentially estimating the true function. So that's um, You can be it can be a really bad estimator, it can be a really good estimator, but it is an estimator of the true function. So that's the,
So
yeah.
repeatedly, like using the same model to create new simulation, won't it oversimplify the original problem that we had at hand? So like,
This is true, but that the reason it is genius is because it works. So
okay,
we in the like this, I'm simplifying a lot of very complicated concepts here for understanding. But you see this 6.7 things bootstrapping does poorly. So that is this idea of bootstrap, like pull yourself up by your bootstrap. There is this example of when you're stuck in a swamp, you pull yourself up by your bootstraps, and it makes no sense because like your other foot is going to go deeper because you do that. But in general, like this, the reason this idea is genius is because it works. Like in a lot of cases, when you simulate this data repeatedly, you fit a new model to the simulated data. You simulate the data from the new model, you fit a third model to this second simulated data, fit a fourth model to the third simulated data, and keep doing that until it converges in a sense. So yeah, I mean,
okay,
I was just as confused as you are, but like it works. More questions?
okay, okay. No, no question.
Okay. So yeah, it's a very interesting chapter. From that we go back to this smoothers, another kind of smoother called spline curves. Splines are piecewise cubic polynomials, which means if you divide them up, they are individually small polynomials combined in a chain to form a long curve. And because they're polynomials, they have these things called basis functions. Your basis function is like a constant term plus a squared term plus a cubic term. Well, constant term, x term, squared, linear term, squared term, cubic term, quadratic term. Anyway, um, so but before basis functions, we get to like how do you fit these polynomials? What is the math underlying them? Where do we use them, and how do they compare versus this whole idea of bandwidth based curves, smoothers that we spoke about, which is actually called kernel regression. Um, so that's very a short chapter, and we're getting towards the end here. So bear with me. Why can I not go to chapter 8? Additive models. Okay, so far we've seen that if you have columns of data, you add a coefficient to each column, and your idea is with linear regression you want to fit each of these coefficients for each of these columns. But why do I need to fix the coefficients? So before, I actually missed explaining this. So what we can do is we have some data, we don't assume any fixed number of parameters. So these coefficients are parameters, weights, parameters, coefficients, whatever have you. Um, and to some extent, yeah, so the concept I missed explaining was parametric versus non-parametric models. So the idea of parametric models is you fix these number of parameters in the model, and then you learn these parameters through iterative updates using this loss function and minimizing this loss function. So yeah, in a very technical sense, what you do is you predict at each time step using the coefficient values you have right now. You predict if you can get the response variable. Response was y, covariates was x, xi are your specific columns in your x, and let's say beta or beta I is the coefficient for each xi. So you want to tune your beta I to achieve a particular optimal value where you can multiply your beta I by each xi, and then obtain an extremely good estimate of your yi. Okay. If anyone is confused by this, please let me know. I can repeat. Um, okay. Assuming not. If not, then one idea is why do I need to fix these beta i's? I have my xi's. I can just let the method find the correct number of betas. What if I need a beta j for a combination of xi and xj? So if I have two columns and there is an interaction between those columns, and I need to represent that interaction somehow because that is really predictive of the outcome. So I'm thinking of a good example to give you. Um, I can't come up with one off the top of my head, but the idea is sometimes some multiplication of some variables are really predictive of the outcome, or we call these interaction terms. And in a linear model, you don't have those, or you have to manually create those terms. So with this idea of additive models, firstly, the concept is you can take a non-linear function of each column. So instead of beta I times xi, you take beta I times fi of xi. And fi is could be a different function for each xi, could be the same, could be just a linear function, identity function. So again, what you're doing is you're adding layers of complexity and saying, look, this already subsumes the original model that you had. So the original model was an identity function. Now we're saying if we change this identity function to anything else, or if we give it flexibility, or we expand the class of models that is contained within our estimator, you're basically saying that if it's a more complex model, I can still capture it with my additive model. And that's what this is called. So we go into additive models, we go into why they're good, why they're bad. And the real point I was trying to get at with, I confused you with additive and non-parametric models. But non-parametric models are basically not fixing these betas and saying, I will discover what betas I need. And the first question that arises is, if we can do that, then why do we do this linear regression anyway? Why can't we just discover linear regression? Well, the simple answer is like discovering takes a lot of computational complexity. And with increasing dimensionality of the data, it's even harder. So it's it's possible, it's not impossible, but as you have more and more challenging data sets to work with, it becomes nearly impossible to actually achieve this non-parametric technique. But nowadays, it's there are workarounds, there are some techniques that work. They're not in the textbook, but just for your knowledge, hopefully I've explained some, hopefully you have an idea of non-parametric versus parametric models, why this matters. And what else do I want to say?
By discovering, are we talking about like just making random guesses till we get it right or something? Like, or like, is it not for something for now?
That's a good question. So by discovering, I basically mean that if within that larger model there exists the true model, which is linear, then you will end up learning that true model. So although this is like a broader class of models than just linear models, you will still arrive at a linear model if given enough training time, data, and computation.
Okay, so basically it's like a subset, like
It's
it can result in this.
a,
Okay.
non-parametrics are a superset of parametrics.
Yeah, exactly.
Mhm.
Thanks.
Yeah, so the typical way people explain it is if the parameters, if you let the parameters go to infinity. But I've always found that very non-intuitive. Like, what does that mean? And if you try to work with it, you'll start to understand that you use functions instead of coefficients. So you learn the right function of your data. But anyway, that's for later. So that's why, like, the first question that comes up with non-parametrics is, why can't we just use those? Like, if they are a superset of models and they can do better than the linear model, then why can't we use those? Well, trade-offs. And I should have actually mentioned, we extensively studied the bias variance trade-off in the first couple of chapters. The bias variance trade-off is, how do I want to explain this with, so you make certain assumptions when
Actually, I
you,
had a doubt.
yeah,
In, yeah, sorry. Actually, I had a doubt in the bias variance trade-off while I was going through the chapter. The assumptions in that, and how they say that because it is deterministic, so they are equal. That is something that actually confused me.
I, I I couldn't hear you very clearly. Could you repeat, please?
Yeah, I said that like in the bias within trade off, when they assume that or they say that a certain value is deterministic and that is why they are equal, like E of I think it was F squared is equal to S squared, so that is because if it's deterministic, so I did not really get that thing in that
Oh,
chapter.
yeah, okay, great. So if I'm saying if I'm flipping a coin 500 times, then can you tell me like and if you say that if I flip a 1, I give you 1 rupee, and if I flip if I flip a heads, I give you 1 rupee, and if I flip a tails, you give me 1 rupee. What do you think after 500 times on average, like how much money will you end up with?
That I feel like probably
I'm
like
sorry.
there are many reasons. Will be equal maybe like I don't know.
You're along the right track. So let me repeat the question, right? So, and this is for everyone, if anyone wants to answer. If I I have an unbiased coin. The coin is like a normal coin, equal probability of heads and tails. That is what I mean by unbiased. And I flip it 500 times, and every time there is a heads, I give you 1 rupee, and every time there is a tails, you give me 1 rupee. So, what do you think is going to be the case? Like, who is going to be out of money after 500 flips?
No one.
I guess both will land up at zero, like initially, how much
Yeah,
they had.
it's like
So what you've
they'll
done,
shed off equal amount how much they will gain, so it will be null by the end. No difference.
correct. So what you all have implicitly done is basically calculated the expected value of winnings in for a random variable. Now, if I say this variable is no longer random, if I say that I have a coin from Cholet where every time I both sides are heads, you don't know that, I know that, and I still make this deal with you, and that is no longer a random variable. That is a deterministic value. Like no matter how I flip the coin, no matter who flips the coin, the outcome will be constant. It will be a heads, and I will pay you money. So at the end of 500 flips, you are going to be up 500. I would be stupid to do that, but you're going to be up 500. So the value, what the point is saying, the point behind like the expected value of a deterministic variable being the deterministic variable is that this is not a random variable anymore. Like the expected value of a variable which has the value 1, which is not changing its value, is going to be 1 no matter what you do to it. Is this Does this make sense?
Yeah, it does make sense. Yeah.
All right. So yeah, I don't want to say more about the bias variance trade-off. We go into that in a lot of detail. Um, and we'll get to it when you come there. But the last topic, well, actually the last two topics, how are we doing on time? Yeah, I think we're good on time. So I'm going to wrap up in 4 or 5 minutes, and then I want to take like a couple of minutes to address questions on get to know more about you guys. So last two chapters. After looking at all of these models, in chapter 9, we come to actually testing regression specifications. And what that means is basically we, sorry, does someone have a question? Okay, if not, maybe mute yourself. Okay, so after looking at all of these models, we come to a detailed chapter on testing them carefully. And by that, I mean, remember how we discussed parametric models and said, okay, suppose we don't place this parametric assumption and use a non-parametric model and fit it to the same data. And technically, can't we discover the true parametric model? Sure, because they're a more flexible, non-parametrics are a more flexible model class to work with. But there is no free lunch. So there is the cost of dimensionality. So super complicated models fitting super high dimensional data is just calling for trouble, right? And fitting non-parametrics takes a lot more computation than parametric models. So in this chapter we like dive super deep into model complexity, sample efficiency, and convergence relative to parametrics versus non-parametrics. And finally, in chapter 10, we break down another assumption, a huge assumption that probably all of us have made at some point in our lives without realizing it, of fixed variance noise. So when you say you have a set of x's and y's, what you do is you say my y is like a function of x plus some noise. And we do that because we assume that either like our measurement taking procedure is not perfect, or that we can never truly discover the correct format. Like there is no perfect solution to any machine learning problem, or if there is, if you're getting 100% accuracy, you're doing something wrong. These are like things you hear, but like you don't understand why. So it goes down to like this assumption that you make about the noise. And what you typically do with noise is you say, I assume my noise is like fixed variance, mean zero, variance one, Gaussian noise. And I'll get to Gaussian distributions later, but it is drawn from a particular distribution, and it has a fixed or a finite variance, um, fixed and finite variance. Anyway, what happens when this is not the case? Like what happens when you're taking measurements? Suppose you're taking measurements in a food processing factory, and like you're taking measurements from like 4 machines, and all 4 of them have been made by different manufacturers. And those manufacturers will have their own problems with the machines. Like the measurements won't be perfect, but the noise will also be different for each of them, because different components work differently even though they do the same thing. So 4 points, same measurements, different noise, and I'm using these different measurements to predict something about my data. Yeah, I guess so. So the idea is like, what happens when our noise is not fixed variance? Well, there is this concept of residuals. Now, residuals in English is like what's left over, right? And in statistics, it is essentially the same thing. When you have y, when you have x and beta, you multiply x and beta in order to get your prediction. And you say, okay, but this is not perfect, so I subtract it from the y, and whatever is left is my residual. So your target minus your prediction is your residual. I skipped over the noise part for a little simplicity, but what you assume is that this residual corresponds to my noise, right? Because I've predicted as much as I could predict, the rest must be noise. And if your original assumption was right, then your noise should not have structure, because it is essentially all the same sort of noise. But when you fit your data, when you arrive at these residuals and you say that, okay, now my residuals have structure, that means that that noise has structure. That means that your original assumption was wrong and you need to do something better. And that gets us to this point of then where you have more noise, you can't predict well, and where you have less noise, you want to predict well. So you start weighting your data, and you say that, okay, wherever my first you fit your regular classifier, you get this noise stuff. You figure out where my noise is high, where my noise is low, and then you say, okay, I will inverse weight. And by inverse weight, I mean wherever noise is high, I don't want to weight that sample high, and wherever noise is low, I want to weight that sample high. And by weighting, what you're doing is telling your classifier, learn this area better and leave that area aside, because that anyway has a lot of noise and I'm not going to predict well. So that leads you to this weighted least squares estimator. And that is essentially what where we stopped. So we've covered all of these. We will have a review of all of these, but it will not be very easy to follow, and you will have to spend a lot of time on this. We are willing to spend the time with you because we're doing the re-review, and I believe there are some students who are also writing up solutions to these chapters. Um, Essentially, we all started off at the same point, myself included. Like, we had no idea about statistics. We did not study theory. At least I speak for myself, maybe the others did. But we got to a point where, okay, we can understand what is going on. We can discuss and figure out what are the important bits, what are the unimportant bits. And he's written the textbook extremely well. So this is what we do every week. We present, we discuss, and it helps me in life. I don't know about the others. So yeah, I'll stop here, and we have about 10 minutes for questions and hopefully a round of introductions before I have to join another call. So questions first. Maybe show of hands, how many of you actually went through the textbook? And I don't mean like read, but like glance through the topics. There is a raise hand option. I should open my window. Okay. I can't see chat. Um, yeah, okay, fair amount. Any particular comments on the chapter? Things you found hard? Not chapter, sorry, my bad. On this, in this review, stuff you could not understand from the explanation I offered. This is to get a sense of what we need to spend more or less time on.
So the part where we you spoke about, like I said, that we won't oversimplification ruin things for the original problem at hand. So that part was a little confusing for me. So that part, if we could focus more.
Okay, non-parametrics, got it. Okay, seeing no further questions, I'll at least, for the new people, could you say 1 or 2 sentences about yourself and quickly tag someone else in the group to talk about themselves? Actually, I should stop recording before this. Okay, stopped, stop share, stop recording.